Hey guys, welcome to this new story. Before we go anywhere, take a moment to get comfortable. Let your body settle into the place you've chosen for the night. Adjust your pillow if you need to. Let your shoulders soften, and let the day slowly loosen its hold on you. There's nothing you need to focus on right now, nothing you need to remember. For the next 2 hours, you won't be asked to think, react, or decide anything at all. In this story, you'll be gently carried on a long, unbroken journey toward the edge of the universe, the farthest distance light has reached since time began. There will be no sudden shifts, no sharp surprises, just a smooth, steady movement forward, meant to help your breathing become slow, and even as you listen with your eyes closed. I'll stay with you at the beginning to guide you in, and then, little by little, my voice will settle into the background as you fall asleep, continuing this journey in your imagination. Thus, as we begin, it continues to unfold in your imagination. As we begin, imagine yourself weightless and supported, safe, and unhurried. Ahead of you lies a dark cloud of gas, colder than any natural place we know, and the faint glow of distant stars barely reaches it. Inside, particles move at their slowest possible pace, almost perfectly still. We'll travel there together, slowly, at a pace meant for rest. For now, just let yourself lie still and allow the journey to begin. Today, we are going to explore the coldest place in the universe, but we will begin here, from the warmth and familiarity of Earth. Notice the surface beneath you, the texture of your seat, the slight weight of your body pressing gently down. You might feel a little tension in your shoulders, perhaps in your neck. Let it ease. Let your attention focus not on rushing, but on observing and experiencing. Now imagine yourself lifting gently from the surface, not in a rush, not like a rocket, but as if the air itself is allowing you to rise. The view shifts slowly. Beneath you, the earth spreads out in soft gradients of green, brown, and blue. Clouds drift across continents, casting shifting shadows that move imperceptibly. As you gain altitude, the air thins, and the warmth you felt closer to the ground begins to fade. You might notice a subtle drop in temperature around you, though still gentle. Every layer of atmosphere above us absorbs and holds heat differently. Lower layers retain the warmth of sunlight, of oceans, of land. Higher up, the energy diminishes, and the air feels cooler, cleaner, almost empty. It is a quiet space, full of subtle differences, each measurable and precise. You are moving from the familiar warmth toward the quiet cold of near space, step by step. As you rise above the clouds, the Earth's shape becomes more apparent. The curvature is subtle but visible. Oceans reflect sunlight with a soft glint, while land masses appear as muted patterns. There is movement here, currents in the water, winds over plains, but it slows in perspective, appearing as gentle flows. Atmospheric layers around you create variations in color, from soft blues near the surface to darker shades above. Each a layer absorbs and scatters light in its own way, affecting temperature. The troposphere, where most weather occurs, holds warmth and moisture. Above that, the stratosphere is thinner, colder, and more stable. You are moving into these higher levels, approaching regions where temperatures drop steadily, even as sunlight continues to reach them. Your body might not feel it yet, but the environment around you is shifting toward the cold extremes we will explore. Higher still, the mesosphere awaits. This layer begins around 50 kilometers above the surface and extends far beyond where the weather occurs. Here, the air is extremely thin, molecules spaced widely apart. Temperature drops quickly. The mesosphere is cold, cold in a way that is far beyond what we experience on Earth's surface. At this altitude, the heat from the sun is less easily absorbed. Molecular collisions are sparse, and as a result, the air cannot retain warmth efficiently. You are passing into a space where the normal rules of touch and sensation start to feel different. The air cannot carry heat as it did below. The motion of particles becomes a slower, more ordered dance. Each molecule, almost alone in its movement, follows the universal laws of physics, carrying energy that is measurably low. This is the first step toward the near zero temperatures of the outer solar system and beyond. Above the mesosphere is the thermosphere. Here, temperatures can rise briefly because of direct solar radiation, but the density is so low that heat energy is not felt in the traditional sense. A single cubic centimeter of air might have enough energy to measure hundreds of degrees, but there are so few molecules that the sensation of warmth is negligible. You are beginning to leave the familiar sensations of temperature entirely. The emptiness becomes more apparent. Space is not cold because it pulls heat away. It is cold because there are so few particles to hold energy. As you continue, you move toward the exosphere, the threshold of space itself. This is the layer where Earth's gravity holds only the most distant molecules. Beyond this, the vacuum begins, and temperatures are dictated by radiation and particle motion rather than air or weather. Here, the cold you will soon approach is not a result of lack of sun, but a fundamental property of the universe in near empty regions. From this vantage, you can observe the Earth as a complete sphere: clouds, oceans, continents, and the thin line of atmosphere wrapping the planet. The warmth below is a small fraction of energy contained within a vast, mostly empty space. You are looking outward, beyond Earth, beyond the orbit of familiar satellites, and soon toward the solar system's outer edges. Temperatures drop as distance increases. Mercury, Venus, and Mars each reflect and absorb sunlight differently, and each maintains a characteristic thermal profile. Earth's warmth diminishes relative to the dark expanse surrounding it. The transition is gradual, but measurable. From orbit to the outer planets, the sun's energy is less concentrated, and energy retained by matter becomes far weaker. As you pass the asteroid belt, a field of rock and ice between Mars and Jupiter, the environment shifts further. These bodies carry little heat beyond what the sun provides. Their surfaces can be measured in tens of degrees below 0 Celsius. Jupiter's massive size affects nearby temperatures, radiating faint heat from its interior. Saturn, Uranus, and Neptune follow, increasingly colder, with surface temperatures far below what we experience on Earth. Beyond these planets, in the Kuiper belt, the solar radiation is minimal. Small at the icy bodies reflect almost no heat. Temperature measurements drop steadily, approaching the extremes where only molecular motion dictates thermal energy. You are now traveling through the sparsest regions of our solar system. The Kuiper belt and scattered disk contain objects smaller than planets, made primarily of frozen volatiles, methane, ammonia, water ice. Heat is scarce here. These objects absorb sunlight so weakly that their surfaces reach temperatures barely above absolute zero. This region is our first step into understanding extreme cold. Energy transfer is minimal. The behavior of molecules at these temperatures is slow, governed only by random motion and weak gravitational influence. No atmosphere here exists to retain warmth. The sensation of cold is absolute, defined by the near absence of energy. You can begin to imagine what lies even further out, in regions almost untouched by any heat source. Eventually, you move beyond the Kuiper belt and into interstellar space. Here, the concept of temperature shifts. Space is not empty in the sense of nothing existing. It contains sparse gas and dust, cosmic radiation, and occasionally stray particles from distant stars. The average kinetic energy of particles is extremely low, corresponding to temperatures near 1 to a few degrees above absolute zero. This is the environment where the coldest natural places exist. Molecules move incredibly slowly. Collisions are rare. Energy is sparse and diffuse. It is in this environment that we will find the Boomerang Nebula, the coldest measured natural location in the universe, far beyond planets, beyond solar influence, in the emptiness between stars. Even here, light from distant stars travels, but it brings minimal warmth. The few particles that exist absorb some energy, but the effect is almost undetectable. The nebula itself, though containing matter, has cooled far below the temperatures we experience anywhere near Earth. Its gas expands rapidly, carrying energy outward, leaving the core regions at temperatures measured at approximately 1 Kelvin. This is colder than any natural place in the solar system, colder than Pluto, colder than the far reaches of interstellar space in most locations. Each molecule in the nebula is almost motionless, a result of the nebula's expansion and isolation. This extreme cold is a natural consequence of physics, of thermodynamics acting over time and space on matter so diffuse that any retained energy quickly dissipates. As you approach this region, consider the scale. Distances are measured in light years. Our fastest spacecraft would take tens of thousands of years to reach this point. Yet, using observation and measurement from Earth, scientists have determined temperature, motion, and composition accurately. This requires understanding radiation, Doppler shifts, emission spectra, and the behavior of molecules in extreme cold. The measurements are indirect but reliable. They tell us about the kinetic energy of particles, the density of gases, and the absence of heat. All of this defines what it means to be the coldest place in the universe, a location where the usual methods of heat transfer, such as conduction or convection, are negligible, leaving only the intrinsic energy of individual molecules to be measured. Here now, at the threshold of our journey's primary destination, we pause for a moment. You can sense, even in imagination, the silence of the environment, the minimal movement, the vast emptiness punctuated only by faint light from distant stars. The cold here is not just a number. It is a state of matter in which motion slows, energy diminishes, and time itself feels stretched because changes happen so slowly. You are present in thought and observation at the edge of known temperature extremes. The journey has been gradual, deliberate, and been entirely factual. Each layer of atmosphere, each planetary body, each icy object has contributed to this understanding. And now, with your attention focused, you are prepared to enter the region where the Boomerang Nebula reveals the coldest natural temperatures measured, a place defined purely by the laws of physics, molecular motion, and the absence of heat energy. We can proceed observing the nebula's structure, composition, and dynamics. You notice that its gas forms a shell expanding outward, thin, and nearly invisible in some wavelengths. The outer layers have temperatures slightly higher than the interior, which is exceptionally cold. Expansion carries energy away, leaving the central region near 1 Kelvin. This expansion and cooling are natural consequences of stellar processes. The nebula is the remnant of a dying star whose outer layers were expelled into space. The gases carry away kinetic energy, leaving a core region that has no internal heat source. Here, the cold is absolute in practical terms, and the behavior of molecules is a direct observation of universal laws. Motion is slow, energy is minimal, and the environment is fully dominated by temperature near absolute zero. You are witnessing a natural laboratory that demonstrates the limits of thermodynamics and the influence of matter distribution in deep space. You feel the enormity of the scale, the extreme cold, and the scientific significance, fully grounded in fact, fully present in observation. As we continue, notice how the warmth of Earth begins to fade beneath you. From this vantage, the surface below still holds the familiar shades of green, brown, and blue, but there is a sense of distance that softens everything. You can see oceans reflecting light, continents stretching out, and cloud formations shifting slowly. Each detail is still visible, yet the energy radiating from the surface is becoming less pronounced. The air around you grows cooler, almost imperceptibly at first, as you ascend. The molecules of the atmosphere become thinner, less capable of carrying heat. You might imagine the sensation as a gradual loosening of the environment's warmth, a gentle reduction rather than a sharp drop. Rising higher, the familiar pressures of the lower atmosphere decrease. The troposphere, where most weather occurs, begins to thin, and the winds you might feel down below are less perceptible. Temperature decreases steadily as sunlight spreads over a larger area, warming less efficiently. The lower layers retain heat from Earth, but above them, the air moves more freely, carrying less energy. You can sense a shift, even in thought, from the dense, tactile warmth of the surface to the cooler, more open environment above. This is a transition from the life sustaining layers into a region where heat and motion are no longer concentrated, a move toward near space. The stratosphere lies above the weather layer, extending roughly 20 kilometers upward. Here, temperatures behave differently. They may rise slightly in some regions because ozone absorbs ultraviolet radiation, but overall the air is much thinner. Molecules are more spread out, so the feeling of heat, if it were possible to sense it directly, would be much less. You are passing through a zone where physical warmth is limited and the presence of matter itself is scarce. The movement of air is subtle, almost imperceptible. Even at this altitude, Earth still radiates energy, but it diminishes with every kilometer. You are leaving the warmth behind in a precise, gradual way, moving toward the cold conditions that define near space. As you move further upward into the mesosphere, the air thins more, molecules are far apart, and temperature decreases again. The mesosphere is colder than any altitude humans normally experience. There are no clouds to retain heat here, only sparse gases moving individually. Radiation from the sun is present, but the lack of density means that the energy absorbed is minimal. The feeling of warmth is nearly gone. This layer demonstrates clearly how temperature depends on both energy input and particle density. You can imagine the molecules moving slowly, each carrying only a tiny fraction of the energy they would have near the surface. The reduction in temperature is not abrupt, but continuous, a natural gradient that illustrates the transition from Earth's warmth to the emptiness beyond. Passing into the thermosphere, you encounter air so thin that traditional temperature sensations would be meaningless. A single cubic centimeter might contain molecules moving at high speed, but there are so few that they cannot convey heat to a human body. The thermosphere is exposed directly to solar radiation, yet the space feels cold because there are not enough molecules to transfer energy. You are entering a region where physical warmth cannot exist as we understand it on Earth. It is a threshold, a bridge between the planet's retained heat and the cold beyond. Here, the transition is both spatial and experiential. The further you go, the less influence Earth has over temperature, and the closer you are to the minimal energy conditions of space. Looking down, Earth appears smaller, the colors muted, the details softened by distance. Light still reflects off oceans and clouds, but its energy has less effect on the surrounding environment. The atmosphere continues to thin, and the temperature drops steadily. You are rising through the layers in a way that reveals how our planet maintains warmth and how it loses energy to the surrounding void. Each layer above the surface absorbs, reflects, or scatters energy differently, creating a measurable gradient. You can see the patterns of heat distribution across the globe, where deserts radiate heat differently than forests or oceans. These variations are subtle but significant, especially as you move toward near space, where the energy differences become more pronounced. As you pass above the stratosphere and mesosphere, you might imagine how the air feels if it could be touched. Molecules are widely spaced, energy is low, and collisions are rare. There is a sense of openness, a lack of pressure, and a diminishing capacity to carry warmth. The Earth below still radiates energy, but its influence decreases with altitude. Even in orbit, above most of the atmosphere, temperatures are not uniform. Shadows, exposed surfaces, and the angle of sunlight create variations that are measurable. Observing Earth from this perspective, you can appreciate the balance between absorbed solar energy, reflected heat, and energy lost to the vast space beyond. This is the beginning of our journey to the extreme cold of the universe, starting with the slow loss of heat that every layer of atmosphere provides. Beyond the mesosphere and into the thermosphere and exosphere, the thinning air and diminishing temperature become more evident. The exosphere, extending thousands of kilometers above the surface, represents the transition into space proper. Here, air is almost non existent, and the few particles present move independently, carrying very little energy. Temperature in this context is a measure of molecular motion, and with so few molecules, the concept of warmth changes. You are leaving behind not only heat, but the medium that conveys it. The environment is increasingly defined by vacuum, radiation, and the kinetic energy of sparse particles. Each step upward reinforces the gradual departure from the warmth we know. From orbit, you can observe the heat profile of Earth. Infrared measurements show where the planet releases energy. Equatorial regions radiate more, polar regions less. Oceans hold heat longer than land. Clouds modulate the energy released. These patterns are observable even from the edge of space. You are witnessing the effects of solar energy distribution, atmospheric retention, and planetary rotation. The cooling is continuous, not abrupt. Every kilometer traveled upward reveals less concentrated energy, less capacity for heat. This is the process by which we leave the warmth of Earth behind, moving into regions dominated by cold and near zero energy transfer. As you move further, you reach the point where the influence of Earth's heat is minimal. The exosphere blends into the near vacuum of space. Particles that once carried warmth now travel alone, rarely colliding. The temperature here is determined more by radiation from distant stars than by the planet below. You are entering a realm where conventional thermal sensations cease. The sense of warmth is gone, replaced by a measurable cold defined by the sparse movement of molecules. It is here that our journey begins to approach its conditions similar to the coldest locations in the universe. You are still near Earth, yet already experiencing the shift toward extreme cold. In this space, you can observe subtle cues of cooling. The planet's reflected light and infrared emissions become weaker. Shadows lengthen. Exposed surfaces in orbit experience rapid temperature changes depending on sunlight exposure. The contrast between sunlit and shaded areas is dramatic, and sometimes hundreds of degrees Celsius. These variations illustrate how absence of atmosphere affects heat retention. Unlike the layers of the troposphere and stratosphere, there's no medium to distribute energy. The experience of temperature here is dictated by direct absorption or emission of radiation. You are witnessing, in a tangible way, the difference between warmth retained by dense air and the cold of space, step by step, as we continue. To leave the warmth of Earth, notice how the gradient of temperature, the thinning air, and the diminishing energy all prepare us for the deeper cold that awaits. The journey is deliberate, measured, and factual. Each layer we pass through teaches us about energy retention, heat transfer, and molecular behavior. From the troposphere to the exosphere, we observe a steady, continuous loss of warmth. Each stage is distinct, yet connected. The transition is natural, governed entirely by physical laws. You are witnessing the unfolding of temperature as a function of altitude, density, and energy distribution. It is this gradual departure from Earth's warmth that defines the first part of our journey toward the coldest place in the universe, preparing both body and mind for the extreme conditions ahead. As we leave near-Earth space behind, the solar system opens before us. The planets and smaller bodies become more distant, and the energy from the sun is weaker. You can still see, sunlight reflecting from planets and moons, but it is less intense than close to Earth. The warmth that Earth provided diminishes quickly, and the environment feels more controlled by physics than by familiar weather patterns. Each step outward reveals how energy spreads and cools with distance. This is a gradual change, but measurable. Even in the vacuum of space, temperature has meaning because it reflects the motion of molecules, however few they are. In this part of the solar system, motion slows, and the kinetic energy of particles is lower than anything we felt near Earth. We pass Mercury first, closest to the Sun. Its surface is dry, rocky, and covered with craters. Temperatures on the day side can reach hundreds of degrees Celsius, while the night side drops sharply. The extreme difference is due to its lack of atmosphere. There is almost nothing to hold heat, so the surface radiates energy directly into space. As you observe, you notice the colors are muted, mostly gray and brown, and the details of impact craters stand out. This planet teaches us how the absence of air and low density affect temperature. Its energy is concentrated where sunlight strikes, but there is no medium to distribute it. Molecules on the surface are heated, but without atmosphere, heat cannot travel far. Venus lies next, its thick atmosphere holding immense heat. Clouds of carbon dioxide trap energy efficiently. Surface temperatures remain near 460 degrees Celsius, hotter than Mercury, despite being farther from the Sun. This contrast shows how atmosphere controls temperature more than distance alone. Dense gases retain energy, distributing it evenly across the surface. Molecules are close together, moving rapidly, carrying energy efficiently. The experience is the opposite of what we just observed on Mercury. Here, motion of particles creates a continuous thermal environment. You can sense in observation how molecular density changes thermal behavior. This comparison helps us understand that energy depends on both input from the sun and the medium that holds it. Mars comes next, smaller and colder. Its thin atmosphere cannot retain much heat. Daytime temperatures can rise modestly, but nighttime brings significant cooling. You can see its reddish surface, craters, and dust storms from afar. The planet's behavior is between Mercury and Venus. Solar energy warms the surface, but the thin air cannot distribute it efficiently. Molecules are more sparse, moving slower on average. The surface energy drops quickly at night. This demonstrates the importance of atmosphere in regulating temperature. The contrast between planets thus highlights the gradient of warmth as we move outward. Each body shows a combination of distance from the sun and local atmospheric conditions, defining the energy environment we observe. As we move past Mars, the asteroid belt appears. Rocks and icy bodies drift sparsely across space. These objects have little capacity to hold heat. They absorb sunlight, but the energy is minimal. Surfaces remain extremely cold. The belt teaches us about small body physics. Without substantial mass or atmosphere, objects cannot retain energy. Molecular motion is slow, and temperature is low, approaching the extremes of the outer solar system. Even small shifts in energy distribution can affect surface temperature. Observing these minor planets gives a clearer understanding of how distance from the sun and size interact to produce cold environments. Beyond the belt lies Jupiter, a massive gas giant. Its thick atmosphere contains hydrogen and helium, and internal heat contributes to warmth. The upper clouds are cold, often below minus 100 degrees Celsius, while lower layers contain faint internal heat. Molecular motion varies with altitude and composition. You can see the swirling cloud bands, the storms, and the faint light reflected from the sun. Temperature decreases with distance from the interior. Motion of molecules slows. As you move outward, Jupiter shows that large mass and internal energy can influence temperature, even far from the sun. Observing the contrast between upper and lower layers demonstrates how kinetic energy and density interact in a planetary system. Saturn follows, similar in composition but colder at the cloud tops. Its rings reflect sunlight, but the main body is far from the sun, receiving less energy. The atmosphere is thin compared with internal mass. Temperatures drop to roughly minus 140 degrees Celsius. Molecular motion is slow, and kinetic energy is low. Saturn's environment provides a clear example of cold in a large gas giant at a significant distance from the sun. Observing the rings, you see frozen particles reflecting light, but the overall energy is minimal. This shows how solar distance and particle composition influence the thermal environment. Uranus lies farther still. A large planet with a faint internal heat source, it orbits far from the sun. Surface, temperatures drop further, around minus 200 degrees Celsius. Hydrogen, helium, and methane gases dominate. Molecular motion is slow. Energy transfer is limited because of distance and low solar input. The visual appearance is pale blue, muted, and soft, reflecting minimal sunlight. You can sense the contrast between Uranus and inner planets. It illustrates how solar radiation decreases with distance and how internal heat can be a minor but measurable factor. Neptune follows, similar to Uranus, slightly more active internally. Cloud tops measure roughly minus 220 degrees Celsius. Methane absorbs red light, giving the blue color we see. The distance from the sun ensures minimal energy input. Molecular motion is very slow. Internal energy contributes only slightly. This region marks the edge of the solar system's warmth gradient. Observing Neptune emphasizes how temperature declines outward and how molecular motion defines what we understand as heat. Energy is minimal, and behavior of particles demonstrates fundamental principles of physics in low-density environments. Beyond Neptune, the solar system thins further. Small icy bodies drift in the Kuiper belt. Pluto is among them, cold and distant. Its surface temperature averages minus 230 degrees Celsius. Molecules move slowly, and energy is scarce. The thermal environment is controlled by minimal solar input, lack of atmosphere, and low density. Observing these objects, you understand how distance reduces energy and how molecular motion is nearly frozen compared with inner planets. This is the outer solar system, a bridge to the extreme cold of interstellar space. As we cross this region, we introduce the concept of absolute zero. This is the temperature at which molecular motion stops completely, minus 273.15 degrees Celsius. Nothing on Earth naturally reaches it, but in deep space, temperatures approach 1 or 2 degrees above absolute zero. Molecules in these regions move extremely slowly, rarely colliding. Energy is minimal. This provides a benchmark for understanding the environment we are approaching. The outer solar system and distant nebulae demonstrate behavior near absolute zero, showing the limits of molecular motion and energy retention. The gradient of temperature through the solar system is continuous. Each step outward shows lower energy, slower molecular motion, and colder environments. The inner planets retain warmth through sunlight and atmosphere. Outer planets depend on mass, internal heat, and composition. Beyond them, small icy bodies and interstellar space approach extreme cold. You can see, even in observation, the way energy dissipates, molecules slow, and temperatures decline naturally with distance. Each planet and minor object contributes to a continuous understanding of thermal behavior, preparing for the coldest places beyond the sun's influence. In this segment of our journey, we notice how energy and temperature change gradually yet predictably. The sun radiates energy outward, but with each additional kilometer, each layer of space, energy disperses. Particles move less, kinetic energy drops, and molecular collisions become rare. This environment is not empty. It contains particles, photons, and radiation, but the energy is vastly lower than near Earth. Observing planets like asteroids and distant bodies, we understand how solar distance, mass, and composition create a thermal gradient. The outer solar system serves as a bridge to near absolute zero conditions, where motion of molecules becomes the defining factor of temperature. Finally, as we continue past Pluto and the Kuiper belt, you sense the diminishing influence of solar heat. Even sunlight is faint here. Molecular motion is slow. Temperatures approach the extremes, though not yet reaching the record lows of the coldest nebulae. This is a natural, continuous transition from the warmth of Earth through the solar system, illustrating the decline of energy and motion with distance. We are crossing the outer limits, observing, measuring, and understanding how the universe cools with distance. Each planet, moon, and icy body provides a data point in this continuous decline toward extreme cold. Our journey continues, moving beyond the solar system toward interstellar space and the regions where the universe approaches its minimal temperatures. As we move beyond Neptune, the solar system stretches into emptier space. The sun's light is faint, and the warmth we left behind is almost gone. This region contains small objects, frozen and distant. We are approaching the Kuiper belt, a zone filled with icy bodies and minor planets. Unlike the planets we just passed, these objects are small, irregular, and scattered. Some are no more than a few kilometers across. Their surfaces are coated in ice, often a mix of frozen water, methane, or ammonia. Sunlight barely reaches them, so temperatures are extremely low, often around minus 220 to minus 240 degrees Celsius. Molecular motion is slow here, and energy transfer is minimal. Even the faint light that falls upon them provides only tiny amounts of heat, insufficient to warm the objects in any measurable way. From this distance, you can see many small bodies drifting silently. They move along elliptical paths, orbiting the sun at a great distance. Collisions are rare because the objects are spread over vast regions. The sparsity of matter defines the environment here. Unlike the inner planets, where gravity, atmosphere, and density create regular patterns, the Kuiper belt is mostly empty. Objects are separated by millions of kilometers, and their interactions are subtle. Some bodies may carry comets or debris. Their motion is slow, and energy is conserved carefully over time. Heat transfer occurs only through radiation, as there is no medium for conduction or convection. The environment is dominated by vacuum and near-zero temperatures. Observing individual objects, you notice their surfaces vary. Some have darker regions, absorbing a little more sunlight, while others are brighter, reflecting what little energy reaches them. These reflectivity differences create minor temperature variations. Even the slightest absorption of energy can be detected in measurements, but it is still extremely low. Molecules in the surface ice move slowly. Gas from sublimation is minimal. The balance between sunlight absorbed and energy radiated back into space maintains the extremely cold conditions. It is a direct demonstration of how matter behaves when heat sources are scarce and density is low. As we continue, we encounter minor planets like Haumea, Makemake, and Eris. Each is coated in ice and rock, maintaining surface temperatures only slightly above absolute zero. Their orbits are distant and elongated. The energy they receive from the sun is minimal. Even during closest approach, the amount of thermal energy is tiny. Molecules in surface ice have little motion. Any gas released through sublimation is slow-moving and rare. These distant objects show us how bodies maintain extremely cold temperatures when sunlight is weak and no atmosphere exists to trap energy. Observing them helps us understand the thermal dynamics of distant solar system objects. Beyond the Kuiper belt lies the scattered disk. Objects here are even more distant and irregular. Their motion is slower, and collisions are even less frequent. Ice and rock dominate their composition. Solar radiation is faint, almost negligible. Energy transfer occurs primarily through radiation. There's no significant atmosphere to conduct or redistribute heat. Molecules remain slow moving, nearly frozen in place. Some of these objects may travel into interstellar space, taking their extremely cold temperatures with them. Observing this region shows how sparsity of matter allows temperatures to approach the limits set by the sun's weak radiation at great distances. Cometary remnants also populate these regions. Small bodies of ice and dust travel along long elliptical paths. When they are far from the sun, their surfaces are frozen solid. Molecular motion is minimal. Sublimation does not occur. Only when they approach the inner solar system do we observe energy absorption and release, and even then, the change is gradual. Most of their lifetime is spent in extreme cold, slowly orbiting the sun or being influenced by distant stars. The physics of their surfaces provides insight into how matter behaves under near absolute zero conditions for millions of years. It is a natural laboratory of cold chemistry and molecular stability. Beyond the Kuiper belt is the Oort cloud, a vast spherical shell surrounding the solar system. Its distance is immense, thousands of times farther than Neptune. Here matter is extremely sparse. Tiny icy bodies, perhaps only meters across, drift almost independently. Collisions are incredibly rare. Temperatures are nearly uniform, approaching 1 or 2 degrees above absolute zero. Molecular motion is incredibly slow. Each particle moves almost alone, rarely interacting with others. Energy transfer occurs only through radiation from the distant sun or other stars. The Oort cloud represents the extreme limit of the solar system, where thermal activity is minimal and molecular energy is near the lowest naturally occurring values. Observing the Oort cloud from a conceptual vantage, you notice the scale. Objects are scattered over trillions of kilometers. Most are invisible to optical instruments. Detection relies on indirect methods, such as observing comets that are perturbed toward the inner solar system. Despite the distance and sparsity, the laws of physics apply consistently. Energy is conserved, molecules move according to universal principles, and thermal motion is predictable based on distance from energy sources. This environment provides a bridge to interstellar space, where temperatures are even closer to absolute zero and matter is even more diffuse. In these outer regions, heat transfer is minimal. Without atmosphere, conduction does not occur. Without significant gas, convection is absent. Radiation is the primary mechanism of energy change, but it is weak due to distance from the sun. Molecular motion dominates what we measure as temperature. Particles move slowly, colliding rarely, and energy is evenly dissipated over time. It is a simple but profound demonstration of how cold can be in the absence of heat sources. Observing these regions helps us understand why the coldest measured locations exist far from stars in low-density environments with minimal energy input. The Kuiper belt and Oort cloud also teach us about timescales. Changes occur slowly. Orbits take hundreds or thousands of years to complete. Sublimation, if it occurs, happens over long periods. Energy exchanges are minimal and gradual. Molecules retain near static motion for centuries. The persistence of cold in these regions shows the stability of near absolute zero conditions over vast periods. This is important because it prepares us to understand nebulae and other cosmic locations where extreme cold is recorded. The principles we observe here are the same principles governing the coldest natural places in the universe. Looking at individual objects in these regions, we notice subtle variations. Composition affects energy retention slightly. Ice reflects some sunlight, while darker surfaces absorb it minimally. Temperature differences are minute but measurable. The molecular motion in ice or frozen gases remains incredibly slow, a fraction of what we see in warmer regions. These variations, though tiny, helps scientists measure and confirm thermal behavior at extreme distances. Observing these subtle effects prepares us to understand how the Boomerang Nebula achieves temperatures lower than anywhere else naturally observed. Throughout this transition, you can see that distance, density, and lack of atmosphere combine to produce extreme cold. The sun is still present, but its effect is minimal. Molecular motion defines temperature. Radiation is the only effective heat transfer. Heat from collisions or internal energy is negligible. Sparse objects in the Kuiper belt and Oort cloud demonstrate these principles in a clear, observable way. The combination of low density, minimal energy input, and slow molecular motion creates temperatures near 1 Kelvin, a prelude to the even colder environments beyond the solar system. Finally, approaching the outer edge of the Oort cloud, we begin to sense the near emptiness of interstellar space. Matter is almost absent. Temperatures approach the record lows of the universe. The distant sun has little influence here. Molecules are slow and rarely interact. Radiation from other stars provides a faint, almost imperceptible energy source. The region demonstrates the principles of heat, energy, and molecular motion at their limits. Observing this space, we see the environment that surrounds the coldest places, preparing the mind and the senses for the journey to the Boomerang Nebula. You feel the sparsity, the stillness, and the near absolute zero temperatures of these distant solar system regions. The gradual transition through Kuiper belt and Oort cloud completes our understanding of the final boundary before interstellar cold. As we leave the Oort cloud behind, our journey takes us farther into interstellar space. The sun is a distant point of light now, barely influencing the environment. Here, the vacuum dominates. Molecules are few and far between. The temperatures we encounter are extremely low, approaching values measured only in specialized observation. It is in this space that we begin to approach the Boomerang Nebula, the coldest known natural location in the universe. It lies roughly 5,000 light years from Earth, far beyond the reach of any spacecraft, yet its presence is measured and understood through the careful observation of astronomers. Its significance is not only in its record low temperature, but also in the way it demonstrates the physics of molecular motion and heat transfer in extreme environments. The Boomerang Nebula was discovered through a combination of optical and radio observations. It appears as a faint, expanding cloud of gas, visible only with sensitive instruments. Scientists noticed unusual features. The nebula was expanding rapidly, and spectral measurements indicated extremely low temperatures. Unlike planets or comets, which retain some energy from the sun, the gas in the Boomerang Nebula radiates heat as it moves outward, cooling far below what is typical even in the outer reaches of space. Detailed study revealed temperatures near 1 Kelvin, roughly minus 272 degrees Celsius. To put this in perspective, this is nearly absolute zero, the point at which molecular motion essentially ceases. The cold is not arbitrary, it is a measurable consequence of expansion and isolation. Visualizing this temperature is difficult because it is so far below anything we experience. Imagine a single molecule moving so slowly that collisions are rare. Energy is minimal, and motion occurs only according to quantum mechanical rules and random residual movement. There's no warmth, no heat that can be transferred by air or contact. The nebula exists in a region where radiation from distant stars contributes almost no energy. Any remaining heat in the gas is carried away as the material expands into space. The result is a natural refrigerator created by the physics of expansion, radiation, and isolation. It is a place where the laws of thermodynamics operate at their most extreme and observable limits. The shape of the nebula gives it its name. Observations reveal a bow-like structure, with the gas forming an envelope around a central point. The gas is moving outward, expanding in all directions. Expansion reduces density, and lower, Density leads to less molecular motion, which lowers temperature further. The light we see comes from scattered and faintly emitted radiation, but it is not enough to warm the gas. Each molecule behaves almost independently, moving slowly in response to expansion and collisions with rare neighbors. The nebula is, in essence, an enormous natural laboratory, demonstrating near absolute zero physics on a cosmic scale. Discovery of the Boomerang Nebula required sensitive instrumentation. Telescopes that measure radio waves, submillimeter, and infrared radiation allowed scientists to detect the cold gas and measure its properties. The rate of expansion was calculated from Doppler shifts in the spectral lines. These measurements, combined with models of molecular motion and energy transfer, revealed temperatures near 1 Kelvin. The methods are precise, indirect, and confirmable. Scientists can predict behavior of molecules, density variations, and cooling rates based on observed expansion. The nebula's extreme cold is not theoretical. It is a directly measurable property, resulting from physical processes operating over thousands of years. The significance of the Boomerang Nebula extends beyond record low temperature. It shows how natural processes can reach conditions that we cannot reproduce easily on Earth. Understanding its temperature helps us comprehend molecular physics in space, the behavior of gases under extreme expansion, and the principles of thermodynamics applied to isolated systems. The nebula demonstrates how cooling is not simply a matter of distance from a star, but also a result of expansion and isolation. It is an example of how matter can approach absolute zero without artificial refrigeration. Observing it informs both astrophysics and our understanding of fundamental physical principles. Temperature visualization in the Boomerang Nebula is striking. 1 Kelvin is nearly absolute zero. It is a temperature at which molecular motion is minimal and kinetic energy is almost entirely absent. Molecules move slowly, rarely colliding. Radiation energy from distant sources contributes only slightly. Any residual heat has been carried away by expansion. The gas behaves differently than anything near planets or stars. There's no warmth, no energy exchange that we feel in everyday life. Each particle moves in near isolation. Observing this, we gain insight into the physical reality of extreme cold. It is a level of temperature so low that most ordinary matter behaves in ways that are unusual compared to familiar conditions. The Boomerang Nebula also provides a clear example of how expansion leads to cooling. As the gas moves outward from the central point, density decreases. Fewer particles mean less molecular interaction. Energy is radiated away into space. Temperature drops naturally, following the laws of physics. No additional cooling mechanism is required. The nebulous cold state is a direct consequence of expansion over time. Observing this process allows scientists to test predictions of thermodynamics, its molecular behavior, and radiation physics in ways that cannot be replicated in laboratories on Earth. This natural process shows the ultimate limit of cooling in the universe outside of artificial experimental conditions. Examining the nebula further, we see that it is not completely empty. Gas molecules, primarily carbon monoxide, hydrogen, and nitrogen, drift through the low-density cloud. They carry minuscule amounts of kinetic energy, moving slowly as they expand outward. Collisions are rare, so energy is shared infrequently. The temperature is determined by the average motion of these molecules, and at 1 Kelvin, that motion is minimal. Any heat transferred by radiation is quickly lost, and the lack of dense matter prevents energy from building up. The Boomerang Nebula represents a near-ideal example of extreme colds maintained naturally where molecular motion defines temperature more than any external input. The discovery of the nebula also highlights the role of observation and measurement in understanding extreme conditions. Astronomers combined data from multiple instruments to determine composition, velocity, and temperature. They accounted for distance, radiation effects, and expansion rates. The result is a reliable picture of an environment unlike any other known natural place. The nebula's temperature is not an estimate. It is calculated from precise physical measurements, confirming the principles we have been following from Earth outward through the solar system into sparse interstellar space and now to the coldest known natural location. Visualizing the temperature again, imagine the difference between Earth's surface, where molecules move rapidly, and the nebula, where motion slows to near stillness. On Earth, molecules in air at room temperature move hundreds of meters per second. In the Boomerang Nebula, molecules move only a few centimeters per second. The energy is almost entirely absent. Any collision or radiation exchange is subtle. There is no warmth to be felt. The cold is extreme, measurable, and consistent across the expanding gas cloud. Understanding this contrast allows us to appreciate the scale of temperatures in the universe, from familiar environments to near absolute zero conditions in natural space. The nebula also teaches us about the persistence of extreme cold. Expansion continues over centuries and millennia. Gas particles remain isolated and slow moving. Energy levels are low. The environment is stable, maintaining near absolute zero temperatures far from stars or heat sources. This persistence demonstrates that extreme cold is not fleeting, but can be a lasting characteristic of certain cosmic structures. It provides a reference for understanding other cold regions in space, guiding our comprehension of molecular behavior, thermodynamics, and the limits of natural cooling. Finally, as we conceptually enter the Boomerang Nebula, the environment feels almost motionless. Particles drift slowly outward. Radiation energy is minimal. Temperature hovers around 1 Kelvin. The nebula is a cosmic landmark, a region that defines the limits of natural cold in the universe. Observing it allows us to connect what we have seen in the solar system, the Kuiper belt, the Oort cloud, and interstellar space, to the ultimate example of minimal molecular motion. It is a location where energy, density, and expansion combine to produce the coldest known natural temperatures. We can now focus our attention fully on the nebula, understanding its structure, temperature, and significance as we continue our journey through the extreme cold of the universe. Entering the Boomerang Nebula, we begin to observe its structure more closely. The cloud of gas stretches outward from a central point, forming a soft, bow-like shape. Unlike the bright stars we are used to, the nebula is faint, its light subtle and muted. The color is not strong, mostly soft shades of gray and pale blue, reflecting the low intensity of radiation. The central region is denser, with more molecules clustered together, while the outer edges are thinner, almost diffuse. The density of gas is very low compared to any environment we have previously seen. Each cubic centimeter contains only a few molecules, drifting slowly through space. The sparsity allows us to observe motion at a scale we cannot see on planets or moons, and yet every movement follows the rules of physics precisely. As we focus on the molecular composition, we notice the dominance of gases like carbon monoxide, nitrogen, and small amounts of hydrogen. These molecules move independently, rarely colliding with each other. The temperature just above 1 Kelvin ensures that kinetic energy is minimal. Even over centuries, motion is slow, controlled by expansion and residual heat. In the densest parts of the nebula, molecules interact slightly more often, exchanging tiny amounts of energy through rare collisions. Further out, these interactions become almost non-existent. The gas behaves as a near-perfect vacuum, but the faint presence of molecules gives it structure. Observing this helps us understand how temperature is defined by motion rather than by density alone. The nebula is not uniform. Gas forms wispy streams and faint arcs, shaped by the expansion from the center and by small differences in initial velocity. We can see layers moving outward at different speeds. Some regions drift slightly faster, carrying molecules away from the central source. Others move more slowly, maintaining marginally higher density. The motion is so gradual that without precise instruments, it would be imperceptible. Yet over decades or centuries, these slow movements define the shape and size of the nebula. Expansion is the primary mechanism driving cooling, as spreading molecules reduce their interactions and lose energy to the surrounding vacuum. Light interacts subtly with the nebula. Photons from distant stars pass through or scatter off the gas. Some are absorbed and re-emitted, but the energy is minimal. We detect this faint radiation through instruments, revealing the presence and motion of molecules. It provides a way to map the density and composition of the cloud. The light is never bright, never warm. Instead, it is a soft indication of matter in space, revealing structure where our eyes alone would see nothing. Observing the interplay of light and gas gives insight into how molecular clouds behave at extreme cold, demonstrating principles of radiation transfer in a near absolute zero environment. As we examine the central region, molecules are slightly denser, moving slowly but more predictably. Expansion creates a gradient. Molecules near the center are closer together and slightly warmer in terms of kinetic energy, while those at the edges are more isolated and colder. The temperature difference is subtle, measured in fractions of a Kelvin, but it is enough to influence motion and distribution over time. Even the faint radiation from the center is minimal, absorbed and scattered almost immediately. This region shows the delicate balance of density, temperature, and motion in a natural structure where energy is scarce but still defined. The outer regions of the nebula are extremely diffuse. Molecules move independently, separated by distances vast compared to their size. Collisions are rare. Energy is almost entirely carried away through radiation. These regions are the coldest, approaching 1 Kelvin, where molecular motion is almost halted. The structure is maintained only by the initial velocities of molecules and the slow outward expansion. Any disturbance from passing stars or cosmic rays is minimal but detectable, influencing motion in tiny ways. Observing this, we see a system in which motion defines the environment more than heat or density. Temperature here is a direct measure of molecular speed. The shape of the nebula is maintained by the consistency of expansion. There is no turbulence as on a planetary atmosphere. Instead, motion is smooth and continuous, almost imperceptible at human timescales. Wisps of gas drift outward along arcs, maintaining bow-like symmetry. Differences in density create faint contrasts that we can detect with sensitive instruments. These contrasts allow mapping of the cloud's three-dimensional structure. The nebula is a physical manifestation of near absolute zero thermodynamics. Its motion, composition, and energy levels combine to create a stable environment, frozen in space, yet dynamic in expansion. Observing the faint radiation from the nebula, we notice emission lines corresponding to specific molecular transitions. Carbon monoxide emits radio waves detectable by telescopes, revealing velocities and densities. Nitrogen shows weak signals in specific bands. Hydrogen, although present, contributes very little to energy measurement. The data provide a detailed view of the cloud's behavior. Motion is mapped precisely, confirming expansion rates and density gradients. Temperature measurements align with these observations, showing the connection between molecular motion, kinetic energy, and thermal properties. The nebula provides a natural example of physics in near absolute zero conditions. Looking at the nebula in 3 dimensions, we can see layers forming as gas moves outward. Denser regions are near the center, thinner at the edges. Each molecule follows a trajectory influenced only by initial velocity, gravity, and rare collisions. The expansion is slow, yet over centuries it shapes the nebula into the observable bow-like structure. There's no uniformity in density, but there is consistency in motion. Every part of the cloud behaves according to the laws of physics, illustrating how structure emerges even in extreme cold. The nebula is a visual and scientific demonstration of molecular dynamics in an almost empty environment. The faint light from distant stars illuminates the outer edges, though weakly. These photons interact with the gas, scattering minimally. The result is subtle glows and shadows, detectable only with sensitive instruments. The interplay of light and gas provides information about density variations and the distribution of molecules. Even in these conditions, radiation is a key form of energy transfer. The nebula's cold, sparse environment ensures that radiation, though faint, remains observable and informative. Light allows us to track motion and understand the behavior of particles in ways that thermal sensing alone cannot provide. In the densest regions near the center, molecules are slightly more energetic, but still extremely slow compared to any environment near planets. Expansion causes a continuous decrease in density and motion as we move outward. Temperature follows this gradient. Molecules carry minuscule kinetic energy, radiating heat slowly into the vacuum. The structure remains coherent because expansion is uniform and molecular interactions are rare but consistent over time. The nebula provides a laboratory for observing these principles directly, allowing us to understand how molecular clouds can maintain such low temperatures for thousands of years without external energy input. Even the edges of the nebula reveal subtle physics. Molecules are widely separated, moving almost independently. Collisions are nearly absent. Energy transfer occurs primarily through radiation, with minimal contribution from neighboring particles. Temperature is extremely low, and motion is slow. Observation of these regions confirms the consistency of thermodynamic principles in extreme conditions. The outer edges provide a transition to interstellar space, where matter becomes even sparser and energy levels are lower. The nebula represents a boundary of near absolute zero conditions within a structured, expanding cloud. Finally, immersing ourselves in the Boomerang Nebula, we can appreciate the scale of molecular motion, gas density, and energy. The cloud is expanding, faintly glowing under the influence of distant radiation. Molecules move slowly, almost suspended. Energy is minimal, temperature near 1 Kelvin, and the structure is defined by expansion and sparse interactions. Observing the nebula in detail provides both a visual and scientific experience, allowing us to understand extreme cold, molecular dynamics, and subtle radiation effects. Every part of this environment illustrates how physics operates under the most extreme conditions naturally occurring in the universe. Here, at the edge of motion and heat, we witness the coldest natural laboratory known to science, a region that defines the limits of molecular energy and thermal behavior in space. As we continue observing the Boomerang Nebula, we can focus on the behavior of individual molecules. Temperature in this environment is defined by motion. Molecules move slowly with very little kinetic energy. Unlike conditions on Earth, where molecules collide constantly and energy is distributed quickly, here collisions are rare. Carbon monoxide, nitrogen, and trace hydrogen float outward almost independently. Each particle follows a straight path unless it encounters a neighboring molecule. The few interactions that occur are weak, transferring minimal energy. Over time, this results in a highly predictable and stable environment. Motion at 1 Kelvin is almost imperceptible, yet it fully defines the temperature. Every aspect of thermodynamics at this scale is apparent. Dust particles are also present, though in very small amounts. These grains are tiny, made of frozen molecules and silicate material. The particles drift slowly, carried by the expanding gas. Their motion mirrors that of the surrounding molecules. Collisions between dust and gas are infrequent, but they help illustrate energy exchange at extreme cold. Even these minute interactions are enough to maintain a coherent cloud structure over long periods. The dust contributes to faint light scattering, giving subtle visual cues that trace the motions of the gas. Observing dust behavior in such cold conditions helps us understand low density environments in ways not possible in warmer regions. The gas dynamics in the nebula are governed by expansion and isolation. There is no convection, as in planetary atmospheres. There is no conduction except during rare collisions. Radiation from distant stars provides a tiny influence, but does not significantly alter molecular motion. Expansion causes the gas to become thinner, lowering the number of interactions. As a result, temperature drops further, stabilizing near 1 Kelvin. The expansion is uniform but slow, so the cloud retains its bow-like shape over centuries. This natural process demonstrates principles of thermodynamics applied on a massive scale, where cooling results directly from molecular separation and lack of external energy sources. Molecular motion can be measured indirectly through Doppler shifts. By observing the spectral lines of gases like carbon monoxide, scientists can calculate velocities. At these temperatures, velocities are extremely low. Molecules drift centimeters per second rather than meters per second as on Earth at room temperature. This demonstrates the connection between kinetic energy and temperature clearly. The lower the motion, the colder the environment. The nebula provides a natural experiment in which we can observe this principle operating at a scale and temperature beyond Earth's laboratories. It is a direct illustration of thermodynamics at its limits. Comparison with Earth-based cryogenics is instructive. Laboratories on Earth can reach temperatures near 1 Kelvin using liquid helium and advanced refrigeration. In these experiments, molecules slow down and motion is controlled through careful isolation and thermal shielding. In the nebula, the same effect occurs naturally, but over immense distances and time scales. There is no external manipulation. Cooling results from expansion and sparse density. Molecules behave similarly to cryogenic experiments, moving slowly, rarely colliding, and exchanging energy minimally. The nebula demonstrates that the physics we study in labs on Earth thus applies universally, even in faraway space at extreme cold. Dust and gas interactions at near zero temperatures are subtle but measurable. Tiny dust grains can collide occasionally with slow-moving molecules, transferring minute energy. Over long periods, these rare events have a cumulative effect on structure and motion. Gas molecules themselves move in smooth paths, rarely deviating. Any radiation absorbed from distant stars is immediately radiated back, keeping temperature low. The cloud remains in a stable, slowly expanding state. These interactions highlight the delicate balance of motion, energy, and structure in an environment where absolute zero conditions are nearly reached. The density of the nebula affects molecular behavior. In denser regions near the center, collisions are slightly more frequent. Molecules exchange energy over time, but it is still minimal. Moving outward, the density drops, and molecules interact even less. Expansion lowers kinetic energy further, and temperature remains near 1 Kelvin. This gradient shows how density and motion define thermal properties. Observing different regions allows us to see the relationship between number of molecules, energy transfer, and cooling. Even in such extreme cold, physical laws are fully in effect, governing every particle's movement and energy. The nebula also illustrates entropy in an extreme environment. As gas expands, particles spread out, increasing disorder. Energy is distributed thinly across vast volumes. Collisions are rare, so energy is conserved locally. The slow motion and minimal interactions make the nebula a nearly ideal system for studying thermodynamic principles at their limits. The behavior of molecules, dust, and gas is entirely predictable within these laws, demonstrating that even at near zero temperatures, The universe follows consistent rules. Observing this allows us to connect cosmic conditions with concepts we can test and model on Earth. Molecular speeds can be visualized conceptually. At 1 Kelvin, a carbon monoxide molecule drifts at only a few centimeters per second. Collisions are infrequent and gentle. Dust grains move similarly, their motion barely affected by the few encounters they have. Radiation provides minimal nudges, insufficient to significantly alter speed. Kinetic energy is almost entirely absent compared with any environment near a planet or star. Observing this, we begin to understand what extreme cold really means. Not simply low numbers on a thermometer, but a state where motion is minimal, collisions are rare, and energy is nearly zero. Even long term processes operate slowly. Expansion stretches the nebula over centuries. Collisions between molecules or dust occur on timescales measured in decades or more. Any radiative cooling is gradual. There is no sudden change, no turbulence, as no convection. Energy moves in tiny increments, and motion is smooth. This consistency makes the nebula a nearly perfect system for observing physics at extreme cold. The slow pace allows detailed measurements and modeling, connecting cosmic behavior with laboratory cryogenics. Observing the nebula provides a bridge between human experiments and natural phenomena, showing how universal principles operate across scales. Gas in the outer parts behaves almost independently. Molecules drift alone, motion controlled only by inertia and rare interactions. Energy is minimal. Temperature is defined solely by this motion. Even faint radiation contributes little. The outer edges approach conditions nearly identical to those simulated in laboratory. Cryogenics at 1 Kelvin. The nebula is thus both a natural example and a reference point for understanding extreme cold. Dust and gas dynamics here illustrate the principles of energy transfer in the absence of atmosphere, conduction, and convection. Motion becomes the primary indicator of temperature. Observation of light interaction is also subtle. Radiation from distant stars passes through the nebula, occasionally scattered by gas molecules or dust grains. This light allows measurement of motion and density, but it is extremely faint. There is no illumination like near a planet or star. Any absorbed energy is radiated away quickly, contributing minimally to warming. The faint scattering reveals structure without altering the extreme cold. The nebula becomes a transparent laboratory, showing how radiation, motion, and density interact at temperatures close to absolute zero. Finally, comparing the Boomerang Nebula to Earth-based cryogenics, the principles match perfectly. So only to our Earth, molecules slow with cooling. In the nebula, the same occurs naturally. Dust and gas interact minimally. Expansion acts as a refrigeration mechanism. Collisions are rare, energy transfer is limited, and temperature remains extremely low. The nebula demonstrates how the laws of physics scale from controlled experiments to the universe itself. Observing molecular kinetics, thermodynamics, and energy behavior here solidifies our understanding of extreme cold, bridging cosmic phenomena and laboratory science. Every aspect of motion, interaction, and temperature in the Boomerang Nebula confirms the universality of physical laws in near absolute zero conditions. As we pause within the Boomerang Nebula, it becomes clear how immense space truly is. The distances between particles, clouds, and clusters are vast. A single molecule might drift for kilometers before ever meeting another. Light from distant stars stretches across thousands of kilometers before reaching the nebula, and the faint glow we detect travels millions of kilometers before instruments can measure it. Time in this environment feels different. Processes that take seconds on Earth, like molecular collisions, occur here over decades or centuries. Expansion unfolds slowly. Motion is minimal. Observing these scales requires patience and attention. It allows the mind to grasp how small our familiar sense of time and space is compared with the universe around us. Every detail of the nebula moves slowly. Dust grains drift outward, molecules expand gently with the flow of gas, and radiation from distant stars passes through almost unnoticed. Energy distribution is minimal. Heat transfer is subtle, primarily through radiation and occasional molecular interactions. Without the dense atmosphere or thermal sources found on planets, energy disperses gradually. Expansion itself acts as a cooling mechanism. The very sparsity of the environment makes motion and temperature intimately linked. Each particle moves according to physical law, and its motion defines energy rather than any external heat. Observing this helps us understand how cold, isolated systems distribute energy naturally across space and time. Looking outward from the nebula, interstellar space begins to dominate. Beyond the edges of this cloud, matter is even sparser. Temperatures approach a limit that cannot be reached in typical laboratory conditions. Molecular motion slows further. Collisions are almost non existent. Radiation from stars becomes the primary form of energy transfer, yet even that is weak. Distances stretch into thousands of light years, dwarfing the size of the solar system we passed long ago. Considering these scales provides perspective. The Boomerang Nebula is both extreme in its cold and in the emptiness that surrounds it. It is a reminder of how the universe operates at its limits and how far matter and energy can be stretched while still following universal laws. Time seems almost suspended. Expansion and cooling occur at a pace that the human mind must slow down to observe. Decades of molecular motion pass for a single observation, yet the pattern remains stable. Gas densities decrease gradually, creating a continuous gradient from the denser center to the thin edges. Motion defines temperature, and temperature defines motion. The slow rhythm of the nebula teaches a different perception of the universe, one where change is measured in centuries rather than seconds, where energy disperses over immense volumes, and where the mind must adjust to observe processes that are invisible on human scales. Energy distribution is uniform in a sense, but extremely minimal. Each molecule carries a tiny fraction of energy compared with anything on Earth. Collisions are rare, so energy sharing is limited. Radiation from distant stars contributes but does not dominate. The expansion stretches energy across space, maintaining extremely low temperature. The physics is clear, isolated. Systems lose energy as they expand, and motion slows. The nebula demonstrates the maximum effect of expansion-induced cooling. Observing this reinforces the understanding that cold is not merely the absence of warmth, but a measurable state dictated by motion, energy, and distance in sparse environments. Visualizing the nebula over cosmic scales, we can see layers moving outward. Denser regions form a faint boundary near the center, while the edges are diffuse, almost imperceptible. The movement of gas and dust is so slow that it would take human lifetimes to notice. Yet this slow motion is crucial. It governs temperature and energy transfer and structure. Every part of the cloud, from central density to outer diffusion, illustrates how energy behaves in extreme isolation. Observing these gradients helps us understand thermodynamic limits and how the universe naturally maintains cold in faraway, low-density regions. The vast distance of the nebula emphasizes the scale of energy dissipation. Photons travel freely, barely interacting with the few particles present. Gas molecules move outward in gentle expansion, carrying away minuscule amounts of energy. Collisions are infrequent. Kinetic energy is almost entirely absent. The uniformity of motion across such distances defines the stability of temperature near 1 Kelvin. The nebula becomes a reference for understanding cosmic cold, providing a natural laboratory to observe how energy spreads and diminishes across extreme space. Time, distance, and perception converge in this environment. A molecule's journey from the center to the edge of the nebula may take centuries. Radiation from distant stars takes thousands of years to reach the nebula. Energy moves slowly. Expansion shapes motion gradually. The human mind, accustomed to rapid change, must adjust to perceive this environment accurately. Observing these cosmic scales brings a sense of grounding. It allows the listener to slow attention, to feel the scale and duration of processes, and to understand how extreme cold arises naturally from distance, isolation, and expansion. Even faint radiation provides valuable information. Photons interact occasionally with molecules, scattering or being absorbed and re emitted. These interactions are rare but measurable. They reveal velocity, density, and distribution within the nebula. Energy transfer remains minimal, maintaining near absolute zero conditions. Observing these subtle effects reminds us that even at extreme cold, the universe operates predictably. Molecular motion, radiation, and expansion combine to create an environment where energy is defined by minimal interactions and extreme distance. The cold of the nebula establishes physical limits. Motion is slow, collisions are rare, energy is sparse, density is minimal. Temperature reflects the lowest achievable state outside of artificial refrigeration. Expansion governs the system. Radiation contributes only subtly. Dust and gas behave predictably. Molecules drift independently. These conditions define the edge of physical possibility in natural space. Observing these limits provides insight into both cosmic physics and our understanding of the universe's structure. We begin to grasp how extreme conditions are maintained across space and time. Reflecting on our journey from Earth to the nebula, it becomes apparent how far energy and motion can be stretched. From the warmth of our atmosphere to the near stillness of molecules in the Boomerang Nebula, we observe a continuum. Temperature decreases as distance and isolation increase. Motion slows as collisions decrease. Energy disperses across vast volumes. This reflection allows the mind to connect familiar conditions with extreme cosmic environments. The perception of scale, time, and motion must adjust to appreciate the reality of near absolute zero temperatures and the limits of molecular motion. Finally, the experience of observing the nebula at this scale encourages mental grounding. The eye follows faint wisps of gas, the mind registers centuries of motion, and the body senses stillness. Understanding energy distribution and extreme cold provides context for all matter in the universe. The nebula is more than a cold cloud. It is a measure of distance, a record of time, and a demonstration of the limits of energy in sparse environments. Observing it helps align our perception of the universe with the laws that govern it, allowing both scientific comprehension and mental calm to coexist in the awareness of cosmic scale. As we begin to move away from the Boomerang Nebula, the faint bow-like structure recedes behind us. The outer wisps of gas thin even further, and molecular motion, while still minimal, gradually shifts with the influence of slight radiation from more distant stars. The cold remains extreme, but expansion slows as we leave the densest regions. Dust grains drift in predictable paths, and the energy of each molecule remains tiny. We can detect subtle changes in temperature, a fractional increase as we approach areas with slightly higher radiation exposure. It is a gentle, almost imperceptible change, enough to notice with instruments, but not enough to alter the serene, still environment around us. Moving outward, the motion of gas becomes slightly more active, though still slow compared with any planetary atmosphere. Light begins to change gradually as we leave the nebula. Photons from distant stars scattered by the sparse gas start to interact more consistently with residual particles. The faint glow becomes less diffuse, sharper in contrast, yet it remains soft compared with environments closer to the sun. The nebula's edges fade, and we enter a region where the sparse interstellar medium has slightly higher density than the near vacuum surrounding the coldest areas. Molecules move just a little faster. Collisions, still rare, occur more frequently than within the nebula. Each encounter carries a tiny fraction more energy. The temperature is still extremely low, but we begin to witness the first steps of reacclimation toward warmer regions. Expansion of the cloud continues to define motion. As we leave the core of the Boomerang Nebula, gas spreads outward at slightly higher velocities. Molecules that were nearly stationary now move with slightly more energy, responding to the faint influence of radiation and pressure gradients. The structure begins to appear less rigid, more diffuse. Dust grains follow the motion, drifting along smooth paths, their speed increasing very gradually. This shift is measurable but gentle. The change in molecular motion allows us to track reacclimation, noting how energy disperses and how extreme cold slowly gives way to conditions that are cold but less extreme than the nebula's center. Temperature changes remain subtle. Even small amounts of radiation absorbed from distant stars increase kinetic energy slightly. Molecules now move centimeters per second faster than within the coldest region. This tiny shift demonstrates how energy propagates through sparse gas. Collisions between molecules become slightly more frequent, allowing minimal redistribution of energy. Expansion still dominates cooling, but the influence of external radiation and slightly higher density begins to balance the system. Motion increases slowly, defining a gradient that transitions from near absolute zero to marginally higher temperatures. Observing these changes highlights how cold regions interact with surrounding space, gradually integrating energy over immense distances. The visual landscape evolves. Faint shadows of gas arcs and dust wisps from the nebula slowly vanish. Light scattering changes subtly. Areas that were previously diffuse become slightly brighter and more defined. Distant stars, once minor contributors, now illuminate the surrounding medium with a faint, steady glow. We can perceive gradients in light and temperature as we move further from the nebula. The environment remains extremely cold, but the increase in energy is noticeable. Motion and molecular behavior respond accordingly. The gradient allows us to witness the transition from the coldest natural place to regions where energy disperses more freely, marking the first step toward thermal reacclimation. Dust grains continue to show minor adjustments in movement. They drift along paths slightly altered by the increase in molecular collisions. Energy is transferred very gradually. Kinetic energy of molecules in surrounding regions rises incrementally. The nebula's structure, once sharply defined, dissolves into more diffuse clouds. Motion becomes more dynamic, yet it is still measured in extremely low velocities. Observing this demonstrates the sensitivity of molecules and dust to tiny energy changes. Even minimal radiation and increased density have measurable effects on motion, illustrating how space adjusts over distances and how cold. Regions integrate with slightly warmer surroundings. As we continue outward, light interactions intensify slowly. Photons from nearby stars begin to scatter more frequently, imparting minimal energy to gas and dust. Motion responds accordingly, molecules accelerating fractionally. Collisions remain infrequent, but are slightly more common than within the nebula itself. The temperature remains low, but is no longer the extreme record seen at the core of the Boomerang Nebula. Subtle gradients emerge, creating a layered perception of energy, motion, and density. The transition is gradual, almost imperceptible to casual observation, but clearly measurable with instruments designed for low temperature detection. The shift in molecular motion parallels our mental perception. As the environment becomes slightly warmer, more structured, and slightly more energetic, attention naturally slows. The mind adjusts to the change in scale and energy, molecular motion, temperature gradients, and light. Distribution combine to create a sense of gentle progression. There is no abrupt transition, energy disperses gradually, and motion increases slowly. Observing this allows for mental grounding. The listener's perception aligns with the slow recovery of energy, providing a natural rhythm that encourages attention to relax. The transition is both scientific and sensory, linking measurement with experience. Expansion continues to dictate motion in this region. Molecules move along trajectories defined by initial velocities and minor energy inputs. Gas density remains low, but increases fractionally as we move toward interstellar space outside the nebula's influence. Collisions occur slightly more often, energy redistributes more readily, and the faint heat from scattered photons adds to kinetic energy. These subtle changes prepare the environment for further gradual warming as we move toward areas of higher density and radiation. The transition demonstrates the interplay of isolation, motion, and energy in extremely cold regions. Observing this process allows us to follow reacclimation from extreme to moderate cold. The faint light, combined with minimal temperature changes, provides visual cues for tracking energy flow. Shadows from residual dust grains shift subtly. Faint arcs of expanding gas appear slightly brighter as molecules gain minimal motion. The transition is continuous and smooth. Energy redistribution occurs naturally, guided by expansion and radiation. Molecules carry the slightest increase in kinetic energy, colliding very rarely. Dust drifts along predictable paths, slowly adjusting to new motion. Each step in this gradient illustrates how cold regions reacclimate towards slightly warmer conditions, offering a direct observation of natural energy integration over vast distances. The observer can note the continuity of motion, from the near stillness within the nebula's center to the slowly moving particles at its outer edge. The change is gradual. Dust and gas accelerate fractionally. Energy disperses gently. Temperature rises imperceptibly but measurably. Motion is smooth, continuous, and predictable. The Boomerang Nebula recedes as a distinct structure. Its edges dissolve into more diffuse interstellar matter. Observing these changes demonstrates how isolated, extremely cold environments adjust naturally. Expansion, molecular motion, and faint radiation act together to transition the system toward higher energy levels without turbulence or abrupt shifts. Finally, as we move further, the environment stabilizes into regions slightly warmer than the nebula's edge. Molecular velocities have increased incrementally. Collisions, still rare, occur more often than before. Dust grains drift, with a gentle response to the subtle energy gradient. Radiation interactions are slightly more frequent, adding to minimal energy redistribution. The extreme cold of the Boomerang Nebula fades into the larger interstellar medium. Observation shows how energy and motion integrate slowly, naturally, and predictably, preparing the mind and body for gradual relaxation. The listener can feel a sense of calm alignment with these slow, scientific processes, easing attention as the environment transitions from extreme cold toward warmer regions of space. As we continue outward, the environment slowly feels more familiar. Molecules drift with slightly more energy. Dust grains follow predictable paths. Light from distant stars becomes more distinct, scattering in ways that our eyes could nearly perceive if we were close enough. The extreme cold of the Boomerang Nebula has begun to fade, replaced by conditions slightly warmer, yet still far colder than anything on Earth. This transition marks a gentle reorientation. From the near absolute zero environment, we now start to perceive distances, motions, and energy in a way that connects back to human experience, even if only conceptually. The mind can begin to sense scale and time in units more familiar to daily life. Looking back at the nebula, its bow shape appears smaller but still faintly defined. Expansion continues slowly. Molecules at the edge of the cloud drift outward, barely interacting. The energy levels remain low, but they are higher than in the core. Observing these patterns allows reflection on the extremes of temperature and motion. From our vantage point, the nebula is a natural record of how space can maintain the coldest conditions in the universe while still remaining dynamic. Expansion, motion, and minimal collisions work together to define this remarkable structure. It serves as a reminder of the delicate balance that governs molecular clouds at the edge of human perception. Distance now dominates our view. The nebula is a faint structure in an immense universe. Stars scattered across vast light years shine as distant points. Between them, empty space stretches endlessly. Light from these stars reaches us slowly, giving subtle cues about motion and density. The mind begins to grasp scale differently, recognizing that every particle, every molecule, exists in an expanse far beyond human experience. Time stretches similarly. Processes that took centuries within the nebula now seem instantaneous in comparison to cosmic timelines. The contrast between human perception and cosmic reality becomes apparent. Observing this, the mind can relax, attuning to the slow and steady rhythm of space. Energy remains dispersed, but gradually more observable. Collisions between molecules occur just slightly more often. Dust grains drift predictably, carrying minimal kinetic energy. Radiation interactions increase in frequency, yet still remain faint. Thus, shifts demonstrate how energy reacclimates after extreme cold, preparing the surrounding medium for slightly warmer regions. Watching this process emphasizes continuity. There is no abrupt change. The universe adjusts itself gradually, with predictable outcomes, dictated by motion, expansion, and radiation. Our attention can follow this steady progression, aligning perception with natural rhythms. The transition from the Boomerang Nebula toward human scale understanding is subtle. Motion is slow, yet measurable. Energy is minimal, but sufficient to track gradients. The structure of gas and dust becomes less defined as we move further into interstellar space. Light interacts more consistently, providing soft, visual markers for observation. Temperature rises fractionally. Collisions, though rare, help redistribute energy slightly. These observations allow a gradual mental adjustment. The extreme cold, once alien and almost incomprehensible, becomes something the mind can contextualize. We can feel a connection between what we understand on Earth and what exists in deep space. Time and motion continue their gentle progression. Centuries of molecular drift within the nebula now seem like quiet moments. Expansion unfolds slowly, yet predictably. Dust grains and molecules move along well-defined trajectories, their energy incrementally increasing as radiation and minimal collisions influence them. Observing this gives perspective. The universe operates at scales and times far beyond human experience. Energy distribution, motion, and temperature changes occur at a pace that encourages calm attention. The mind aligns with these natural rhythms, observing without urgency, understanding without distraction. This creates a sensation of stillness, even within a system in motion. Light now plays a larger role in perception. Photons from distant stars interact more frequently with molecules and dust. Scattering events increase slightly, enhancing faint glows and subtle visual textures. Energy transfer remains minimal, yet sufficient to mark the transition from extreme cold toward warmer interstellar conditions. The universe reveals gradients that allow the mind to track motion and temperature subtly. Observing this, we feel an awareness of scale, motion, and energy, all while remaining calm and centered. The journey through extreme cold begins to fold gently into our human understanding, bridging cosmic phenomena with personal perception. Reflection on the experience is natural. The Boomerang Nebula demonstrated the limits of cold, the slowest molecular motion, and the smallest energy exchanges observable in a natural setting. Expansion governs structure. Collisions are minimal. Radiation is faint. The surrounding interstellar medium gradually absorbs energy, allowing for small increases in motion. Observing this transition highlights the relationship between isolation, energy, and temperature. From human scale, we see the nebula as both distant and near, extreme and relatable. The mind can now reconcile what was once alien with intuitive understanding of motion, time, and energy. Gradually, the outer regions of the nebula and the surrounding interstellar space begin to dominate our perception. Molecular motion continues to increase incrementally. Dust grains respond gently. Light interacts more noticeably with sparse matter. The environment becomes subtly warmer. Observing these changes, attention naturally slows. The mind adjusts to the faint, yet continuous increases in energy, aligning with the gradual reacclimation process. The extremity of cold fades into a backdrop, leaving the human mind with a sense of connection to the universe and its continuous, predictable processes. Scale, time, and energy blend in our awareness. The mind can perceive distances in light years without strain. Processes that span centuries appear comprehensible in gradual observation. Energy distribution, motion, and temperature follow patterns that are steady and predictable. The extreme cold of the nebula is no longer immediate, yet its significance remains. We have observed the lowest temperatures found naturally, understood motion at near absolute zero conditions, and witnessed how energy, distance, and time define physical limits. These impressions linger, allowing for a calm sense of comprehension and closure. As the perspective expands further, motion and energy continue to normalize toward interstellar norms. Collisions are slightly more frequent, radiation interactions gently increase, and dust and gas carry modest energy compared with the nebula's core. The transition is seamless. Observing these incremental changes encourages attention to fade naturally. The mind, aligned with the gradual adjustments of motion and energy, can begin to relax fully. Observation is no longer urgent. Attention slows. The journey remains continuous, but the listener's focus can recede gently, leaving the universe in motion beyond immediate awareness. Finally, the vastness of space comes into the foreground. The nebula is now distant, its structure a faint, elegant mark against interstellar darkness. Dust and gas have integrated partially with surrounding space. Energy distribution continues subtly. Light continues to interact softly with matter. Molecular motion, while slightly faster than within the nebula, remains low compared with familiar conditions on Earth. Observing these patterns allows the mind to reflect, recognize scale, and appreciate extreme cold, time, and motion. Human perception has returned, calibrated to cosmic rhythms, aligned with gradual energy changes, and ready to release focus. The journey closes with gentle observation. Molecular motion, expansion, and energy remain measurable but imperceptible without instruments. Dust and gas drift along predictable paths. Light, faint but consistent, marks a subtle gradients. The Boomerang Nebula, extreme in cold and time, has been observed, understood, and reflected upon. Distances have been measured conceptually. Energy and motion have been traced from near absolute zero to slightly warmer regions. Time has been appreciated across scales. The mind, guided gently by these observations, begins to release attention, aligning perception with the steady, calm rhythms of the universe. Our perspective now bridges cosmic extremes and human scale. We have observed extreme cold, minimal energy, and near still molecular motion. Expansion and radiation govern interactions. Dust and gas respond slowly and predictably. Distances and time span centuries and light years. Attention can fade gradually, following the rhythms observed. The mind can rest in alignment with these principles, leaving the universe open-ended yet comprehensible. Observations of energy, motion, and temperature integrate with perception, creating a gentle sense of closure while maintaining awareness of the vast, slowly moving cosmos. Finally, as the voice of observation recedes, the mind remains attuned to the patterns we have witnessed. Extreme cold, near absolute zero molecular motion, expansion, and faint radiation are understood in context. Energy distribution and motion follow universal rules: distance, time, and scale are appreciated. The nebula fades into a conceptual backdrop. Attention drifts naturally, aligned with the gradual progression of energy and motion. The journey remains open in the listener's mind, yet perception has returned to a scale we can relate to. Observation ends gently, leaving space, time, and cold to exist quietly, continuously, and without abrupt closure.